In this work, we present the first one-stage monocular RGB-based arbitrary hands reconstruction method. In ACR, given a monocular RGB image as input without any preprocessing or detection, it'll capture the 3D hands reconstruction in the scene without any external information, which is a step forward that goes beyond all the other hand reconstruction methods. This enables more applications, such as in full body motion capture. And ACR is the only one that can do one-stage hands reconstruction under arbitrary scenarios without any input constraints that all the existing methods suffer from. Our key ideas here are representation disentanglement and collaboration. As the first one-stage method, we adopt the pixel-level representation. Second, we learn a stable representation for two hands. We first do a representation disentanglement for hands and hand parts with Gaussian center map and segmentation. Finally, we will do a cross-hand prior learning with an intention collaboration. In all the previous works, they typically use a two-stage pipeline to learn a highly entangled bounding box level representation. They require cropping the two hands in one box while keeping the region large enough, which is not always possible, and it's a very undesirable property in applications. Moreover, this representation is always ambiguous and fragile under challenging cases and affecting other hands when one of them is missing or separated. And moreover, their hand part representations are also entangled, which will cause instability under occlusion, such as in the figure 2, when a single hand part is missing, both of the two hands will be interrupted, which indicates that we need to further disentangle the hand parts. Comparing to that method, our arbitrary hands reconstruction method has more desirable properties for real-world applications to handle arbitrary challenging cases. Given a raw image as input without cropping, we completely forego the entangled bounding box level representation and adopt the pixel level representation method. And for each of the pixel in the feature map, we will regress the manual parameters and the weak camera parameters. So, the first key idea is to disentangle the two hand representations. Instead of cropping the image bounding box, we represent the hand by only one pixel, using only the hand center. We represent the center with a Gaussian heat map with a repulsion field to push them away, and then the global representations can be extracted. With this kind of disentanglement, we are no longer suffering from the limitations of entangled representations, such as the need of a bounding box and a hand detector. And the hands are no longer affecting each other. For example, when they are getting separated, other method will either completely fail or degenerate because of the entangled bounding box level feature. But our method will no longer suffer from this issue, so we have the highest degree of freedom, and it's the most practical one for arbitrary scenarios. So, in order to be stable under occlusion and truncation, our second idea is to further disentangle the hand parts representation to release the interdependencies between parts. And we achieve this by utilizing the hand part segmentation as a soft attention mask by doing the spatial softmax, and we regress the parameters for each joint, only use the feature corresponding part. So, now the hand parts are no longer entangled, and it'll be very stable under occlusion and truncation. Finally, to model better interaction, we adopt a novel strategy to strengthen the interdependency only when the two hands are interacting with a threshold like this. And in this case, we learn the cross-hand interaction map, and then we do a reverse query using the center position of the other hand. And there is also an intensity factor related to the Gaussian kernel size to adjust the strength. Finally, all these three kinds of representations are collaborated to regress the final mana parameters and the weak camera parameters for each hand.